First off, Kris, you just want to tell us a little bit about your own personal background, like what you did before you came to Novi, what your educational stuff is.
Sure. I received a PhD from the University of Texas at Austin in geological sciences. For my PhD, I studied methane hydrates and carbon dioxide hydrates. And in particular, we were trying to understand how to store carbon dioxide as hydrate in deep marine environments or subarctic environments while also producing methane hydrate for profit. I finished in 2018, and after that, I was a data scientist at a small startup called Slingshot Aerospace. And I was there for about 9 months before joining Novi in, I guess it was March of 2019. Does that sound right? Yeah, I think that's
just before me.
Yeah, exactly. Like 6 weeks, maybe.
Congratulations on 2 years.
Yeah, right. Thank you. Thank you.
That's what in startup years, that's like you've been here for 15, right?
Oh yeah, yeah, definitely. How many sprint cycles is that? Way too many. Over 100 at least.
Yeah. Excellent. Yeah. Well, it's obviously you have a lot of strong contributions to Novi. So the reason we're talking today is because of the forecast uncertainty, which you've been doing a lot of work on pioneering Novi for. When did you start your work on that? 6 months ago, 9 months ago, something like that?
Let's see. I think it was over a year ago. It was in the early part of 2020. And we were trying to understand how to do it better than previous methods that had basically failed.
Yeah.
We were using a lot of trees for estimators, and that's still the case. So random forest or extra trees, et cetera, XGBoost. And we were trying to bootstrap our way to some uncertainty profiles, and that was really cumbersome, computationally expensive. And we stumbled upon this idea, conformal inference, that seemed promising, and it has turned out to be quite fruitful. So we implemented that for our pre-drill forecasts, and then found some additional wrinkles we could add and fold into that to make it really productive for our PDP forecasts.
Excellent. So, I mean, why were you so excited about this new methodology that we developed? Why is forecast uncertainty such a difficult problem, with current methods?
Yeah, well, for a bootstrap, what that means is we're basically building in number of models, and you need to build a lot. So you could say for a model that has 5,000 wells, maybe you need to actually still build 1,000 individual models to give some sort of sense of uncertainty. And that becomes really expensive, especially when building one model takes a couple of minutes. If you're also folding into that whole process, hyperparameter tuning, feature selection, suddenly you don't have the compute power to do that effectively. With conformal inference, we had found a special variation of it called split conformal inference, where we basically just build two models. One is about half the data set, and then the other model is used to evaluate how good we did on the other half. And with that, with only two models as opposed to 1,000, we get most of what we need. And that's phenomenal.
Awesome. Yeah. That sounds like I don't want to go out and train like 1,000 different models to get an uncertainty. That's good. Yeah. So what are the main reasons that you hear coming from our customers that they're interested in the uncertainty around our forecasts?
Yeah, I would say it's the same reason that anyone would ever want uncertainty around a forecast. So I would say from everyday life, you are already incorporating uncertainty implicitly in a lot of things that you do, and sometimes explicitly. So as an anecdote here, I'd say I'm an avid skier. I recently moved to Montana so that I could ski on most weekends. And at my local place, I can be there in 45 minutes, which means I can wake up early in the morning and I can check the weather forecast and decide if the snow is going to be good and the conditions are going to be right. But that's maybe only a couple hours in advance, and I still don't actually know what's going to happen. The weather forecast might say there's going to be 1 to 7 inches of snow or absolutely none. And that matters to me, especially if I'm not trying to ski locally. I'm trying to ski maybe out of state, and that requires an Airbnb reservation. That requires driving and anticipating what the climatology is going to look like weeks in advance. all that carries with it risk that I want to be able to incorporate in my decision-making process. And the same is true for these operators. If we're forecasting 1 quarter in advance, there's going to be a certain amount of uncertainty associated with that, and it's probably going to be small, but it's not zero. We can't just provide a number to say this is exactly what we think is going to happen. We have to provide a range to make it useful. And now as we forecast not 1 quarter in advance, but maybe a year in advance, 2 years in advance, that uncertainty profile should grow. And as that uncertainty profile grows, so should the decision-making process and the risk evaluation.
Awesome. That's a good metaphor. I'm sure lots of our, as I've seen from Twitter and social media, it seems like the entire oil field decamped to the slopes this winter. So I'm sure that's going to hit home for a lot of our engineering and executive customers.
Totally.
Yeah. So, we've, one thing that we do hear a lot of times when we bring up this uncertainty that we produce is a lot of people seem to have this idea of like some kind of a Monte Carlo as their traditional way of estimating what the uncertainty for a forecast could be. So can you give us a little compare and contrast between our method and a Monte Carlo?
Yeah. I respect the Monte Carlo method a lot, and I like it in specific use cases. One of the backbones of that and the requirement, especially of Markov chain Monte Carlo, is that you have a parametric model. And what I mean by that is like a linear model is a parametric model where you say, I'm going to apply a certain weighting to this feature, that feature, et cetera, and then linearly combine them to produce an output. Any parametric model is doing that, not necessarily in a linear way. So there could be transformations internally that occur, such as in a neural network where you're feeding in linear combinations that go through a nonlinear function and then another layer, et cetera. For MCMC, you're basically just varying sets of those internal parameters and evaluating the space of outcomes to see which of the parameter sets is most advantageous for you. And if you do have a parametric model, that's a really good idea. For us, we found a lot of success with these tree-based models, which are non-parametric, in the sense that what you do instead is you look for corollaries that relate to your well of interest. And you say, I've got 6 wells over here, 6 wells over there. They're very good and similar wells to the one that I'm trying to predict on. So I take an average of them. And because of that, the nature of the way that we make that prediction, that means we can't really use MCMC, and we have to use some other methodologies such as split conformal inference or bootstrapping that allows us to get at the same variables. And split conformal inference, as I stated earlier, is really our computationally efficient way of doing that.
Yeah, that sounds pretty powerful. If my understanding is correct, another big advantage of our method is that it's actually measured against actual results on a holdout set. You can perturb the different parameters, whether that's in a neural network model or in an ARPS fit, to get some idea of what the distribution is, but you still have to make some assumptions about what the distributions of the parameters are, correct?
Yeah, you do and you don't always. So I'll modify that question a little bit to say that you can set it up that way where you set all of your data into the uncertainty creation mechanism, and then you go out into the world and you just blindly hope that it works.
Yeah.
You can also set it up such that you leave some of that data out and say, I'm going to build my uncertainty quantification on 80% of my data, and then 20% of it is just going to be out there in the ether, so that then I can evaluate and see how well I did on it. So that's an evaluation technique used in machine learning a lot, and you can apply the same technique in uncertainty quantification. What we do specifically at Novi, though, is we ensure that that 80% that we start to build anything on is sequenced in time. So we use past data or intervals of past data to then make predictions and uncertainty forecasts on future data, so that then we effectively emulate the process that any operator would do with our software. So then we provide a nominal coverage, as we call it, of the forecast. So we're saying, if you want your P90 and your P10, that's effectively like saying, I'm going to miss out on 20% of that. And we guarantee it with our simulation of past trained, forward-looking future predictions.
Yeah, that's a really good distinction that sometimes we lose sight of in the oil and gas industry, that everything that we're making forecasts for has a time basis. So could you draw a little distinction between, what does the error look like on the holdout set for my entire data set versus for a single well?
Yeah, I think it totally depends on the data set and the variables of interest within that data set. But effectively, when you're trying to aggregate on a specific IP day or a number of forward forecast steps, you often have to reduce that to some sort of statistic. So you might say, I'm going to look at the median area of all of the wells of my interest at this IP day or at this forecast step. And it gives you some percentage of how far you might be off or a number of barrels, et cetera. And you might even then expand that to say, I don't want to just look at P50, I want to look at P25, P75. But as you aggregate that, it's really only telling you how good model A is against model B. And you would hope that model A also on the individual level, if it's better than model B, gives a tighter uncertainty band on every individual forecast. But the error that it has, that it holds, does not necessarily relate to the individual well, where the individual well is dependent on each specific feature and how that feature is part of the collection and distribution of all the rest of the features. So for instance, if you're going to make a forecast and you're going to introduce some proppant that is at the fringes of the profile of the proppant that you've seen in your training, you should have a really big uncertainty profile, even if your model is incredibly accurate, because your model saying it's incredibly accurate meant that you were evaluating on the distribution of proppants that you had already seen.
Yeah, so in some ways what you're saying is that, the model may be extremely confident in its forecasts for a well, which is very similar to the other training data that it's seen. Whereas if you send it something totally new, that it might have huge uncertainty. Just like if your meteorologist forecasting your snow conditions up in your local Montana mountain, if you ask the same meteorologist to give you snow conditions down in New Zealand, that person might have a lot higher uncertainty about the forecast that they're making for how many inches of snow you're getting.
Yeah, absolutely. And sometimes we call these like exogenous features, or from an operator's point of view, it's interventional choices that have been made. The uncertainty should reflect the degree of, we'll say, difficulty or the degree of variation against the norm. And we do bake that in. We ensure that the predicted forecast uncertainty we have accounts for every individual feature that you're putting into the model, in addition to the past production of that profile. So you could end up with high uncertainty because the forecast or the actual previous production is erratic, or because you're introducing a feature that is really far from the behavior seen by the model.
Yeah, interesting. So what are some of the applications that you're hearing about from our customers for these type of uncertainty bands or confidence bands?
I think the primary use case is evaluating risk. So if you're going to go out and you're going to drill X number of new wells, and you're looking in a geographical fringe area, you kind of want to know how good is the model that you thought was good, but in an area that you don't actually have much experience in. So you're extrapolating beyond the bounds of the data or right at the edge of the bounds of the data. Or what you might be doing is evaluating your entire inventory of wells, and you want to go X number of quarters into the future and project revenue. The revenue can't just be a finite number. It needs to be a range of possible numbers given everything that you know. So they're using our uncertainty forecast to determine what the bounds on future revenue might be.
Yeah, super interesting. So is this stuff like already in our products right now?
It absolutely is. It is a standard feature in our products, and it can be used for pre-drill wells or PDP wells. And it's configurable to the point, may have to check on this, but I think you can apply two different sets of confidence interval brackets. I think that's our limit right now. So if you were interested in the upper and lower 10%, you could ask for that, or the upper and lower 25%, you could also simultaneously ask for that.
So somebody might want to get like some idea of what the tails of the distribution of any given forecast is, for maybe understanding what their risk is, but then maybe a better idea of what the middle of the distribution looks like for, let's say, per well economics or offtake planning or something like that.
Yep. Yeah. In our point of view is we provide as much information as possible so that the person asking for the forecast can then determine what application that information is useful for, how they may want to use it, and then, as you stated, to be able to use different parts of it for different use cases.